What I'm going to talk today is about greedy approximations with regard to multivariate basis with the tensor product structure. And this is joint work with my advisor, Temlyakov and Peixin Ye. So first, some notations. Let X be an infinite dimensional separable Banach space equipped with null, and let psi be a normalized basis for X. And for a given f in X, we define the best m-term approximation with regard to this basis psi as follows. Sigma m of f psi is defined as the infimum over the arrow of f minus summation over k in lambda bk times psi k, where this infimum is taken over all coefficients bk and the index set lambda with cardinality n. Now for a given element f in X, we consider the expansion of f. And we call a permutation row with rho j equals kj of the positive integers decreasing, and the right row is in D of f if the decreasing rearrangement of the coefficients f satisfies this relation here. And we define the mth greedy approximant of f with regard to the basis psi, corresponding to this permutation row as follows. Okay, and where these ckj's are the decreasing rearrangement of the coefficients of f. And the following concepts and theorem of greedy basis have been introduced or proved by Conditionality and Temlyakov in 1999. The first definition is we call basis psi a greedy basis if for every f in X there exists a permutation row in D of f row, D of f such that f minus gm of f is less than or equal to some constant times the best m-term approximation of f, where this constant is independent of f and m. And the next definition about the unconditionality of basis psi is well known. Okay. And now we call a basis psi in a Banach space X to be democratic if for any two finite sets of indices p and q with the same cardinality, we have the following relation, and where this constant d is independent of p and q. And the following theorem, this theorem, which was proved by Conditionality and Temlyakov, characterizes the relation between these three concepts. Okay? So a basis psi is greedy if and only if it is unconditional and democratic. So next we will look at some direct and inverse theorems. We start with the wavelet basis, and we let H to denote the univariate case Hart basis and normalized in L2, and we denote HP to be the Hart basis H3 normalized in LP. And we let HPD to denote the tensor product of the univariate case, the univariate Hart basis. And it is known that the tensor product structure of multivariate wavelet basis makes them universal for approximation of anisotropic smoothness classes with different anisotropy. It is known that by Temlyakov's 2 paper in 1998 that HP is greedy basis for LP when p is between 1 and infinity. And okay, the following sentence is kind of misleading, but what this says is basically the tensor product of the wavelet basis is not a greedy basis in general. It is a greedy basis only when p equals 2. Now we will use the notation A and F to for the decreasing rearrangement of the coefficients of F. Okay. And the following characterization theorem has been established by Temlyakov. So for D equals 1, P between 1 and infinity, and Q between 0 and infinity, the following, for any positive R, we have the following equivalence relation, okay, like this. And this theorem, the proof of this theorem was based on the following two lemmas. So AM of F P is less than or equal to some constant depending on P times the best n terms approximation times n minus n to negative 1 over P. And for any sequence of monotomally increasing of non-negative integers, we have the following relation like this. So it's natural to think about the following generations in two directions. The first one is because we know this HP is a greedy basis, so we can extend. One can extend the previous theorem to a general greedy basis. And the second generalization is one can generalize HP to the tensor product of HP, which is done by Comment and Temlyakov in 2004. Now, what we do here is we take one step further. We generalize it to the tensor product of greedy basis. So, it is based on the following theorem, which was proved by Characterization and Picard and Temlyakov in 2006. So for P between 1 and infinity and psi be a greedy basis for LP, then for any index set with cardinality M, we have for P between 2 and infinity the following relation here. And for P between 1 and 2, we have the following relation here. And it is known that these log factors are short. Now this is our result, parts of our result. Okay. For any positive R and for any real number B, we have the following relation. The best M term if for the best M term approximation that is bounded above by m plus 1 to negative r times log m log of m plus 1 to negative b. This implies an is bounded above by n to the negative r minus 1 over p times log of m plus 1 to the negative b when p is between 2 and infinity. And if these coefficients an satisfy this condition here, if it's bounded above by n to the negative r minus 1 over p times log of n plus 1 to negative b, then this implies the best m term approximation of f is bounded above by m plus 1 to the negative r times log of m plus 1 to negative b plus one extra term HPD, where this HPD is d minus 1 times the absolute value of a half minus 1 over p for p between 2 and infinity. Okay. So here I only listed the case when p is between 2 and infinity. The case p is between 1 and 2 is similar. But if I list them here, this page will be messed up. Okay. So the proof of this theorem 2.2 follow from the following analog of lemma 2.1 and 2.2. If you compare this lemma with 2.1, it's just we replaced the h here by psi of d for the case p between 2 and infinity. The main difference here is for p between 1 and 2. Okay. We replace the h by psi of d, and we have one extra log term here. And also for this lemma 2.4, if you compare it with lemma 2.2, So this is just we replace h by psi d, and we have one extra log term here for the case p between 2 and infinity. Now, as an example here, to illustrate how our results can be applied to some function classes, we consider the following function class. Okay. So first, some notations. For a given subset of x, we define the best m-term approximation of this set of functions to be the supermum of all f in this f over the best m-term approximation of f. And we define gm of f per psi to be the supermum taken over all f in capital F of the arrow of the greedy approximation here. Now, for r greater than 0, we define the following function class: fr of psi to be all the collection of all these function f such that its coefficients after decreasing arrangement satisfy this relation here. And now, if we let psi pd to be the tensor product of Haar basis, and for p between 2 and infinity r greater than 1 over p, we can prove the following relation. Okay, here, the greedy approximation on this function class is of the same order as the best m-term approximation on this function class, which is m to the 1 over p minus r times log m to the hpd, in case p between 2 and infinity. And in case p greater than 1 and less than or equal to 2 and r greater than 1 over p, we have this relationship. Okay, they are of the same order, which is m to the 1 over p minus r. And this is all I want to present here. And, thank you.